In our earlier videos, we focused on the characteristics of carboxylic acid derivatives. Now we're going to look at reactions of carboxylic acid derivatives. Carboxylic acid derivatives react with a variety of nucleophiles to give acids or esters or amides or aldehydes or alcohols. First, we're going to look at nucleophilic acyl substitution that converts carboxylic acid derivatives into other types of carboxylic acid derivatives. And then in later videos, we'll look at some other reactions of carboxylic acid derivatives. In earlier chapters, we've spent plenty of time looking at how aldehydes or ketones react with a nucleophile. So a nucleophile can share its electrons with the carbonyl carbon, pushing these electrons up onto the oxygen, giving us an intermediate that looks like this. From here, there are a couple of possibilities. This might grab off a proton from water, for example, and that would give us this. Or if the carbonyl reforms, then these electrons come back in here, and what's going to happen? The R group is not going to leave, so the only possibility is that the nucleophile leaves again. So what types of nucleophiles have we seen? If we have a Grignard or an organolithium or a hydride, in these cases the nucleophile is going to add, but it's not going to be kicked back out again. So these are irreversible nucleophilic addition, and then the O- will grab off a proton and we end up with an alcohol. If the nucleophile is an alcohol or a cyanide, then these are reversible nucleophilic addition. So depending on the position of equilibrium, the nucleophile can add and the nucleophile can be kicked back out again. But the R groups are not going to be kicked out. Next, let's consider a carboxylic acid derivative. So one of the features of a carboxylic acid derivative is that they have this Y group, which is capable of stabilizing a negative charge. So when a nucleophile adds, shares its electrons with the carbonyl carbon, pushes these electrons up onto the oxygen, we get an intermediate that looks like this. Now there's going to be some differences in terms of proton transfer, but a next step is that these electrons can reform the carbonyl and it can kick out the Y group as a leaving group. Remember, because carboxylic acid derivatives have a Y group that can stabilize a negative charge. So this gives a new carboxylic acid derivative where Y- is pushed out as a leaving group. So while aldehydes and ketones undergo nucleophilic addition, carboxylic acid derivatives undergo nucleophilic acyl substitution. Overall, what we're looking at is the Y group is substituted by a nucleophile. So this is nucleophilic acyl substitution. As we consider nucleophilic acyl substitution reactions to interconvert the different carboxylic acid derivatives, there's a number of different reactions we're going to be looking at. Some of the most important ones, so for any carboxylic acid derivative, it can undergo hydrolysis to give a carboxylic acid. A carboxylic acid derivative can react with an alcohol to give an ester, or carboxylic acid derivatives can react with an amine to give an amide. So these might be the most common or the most useful, the most synthetically useful reactions, but we're going to take a look at a wider variety of nucleophilic acyl substitution. Now let's try to compare different carboxylic acid derivatives, and for now we're still going to keep this generic, but we have some group that can either pull away electron density or release a little bit of electron density. So if we have a Y group that pulls away electron density, then this carbon is going to have a big partial plus. So having this group is going to make the carbon more electrophilic, which makes it more reactive, which makes it more susceptible to nucleophilic attack. In comparison, if we have a group that can release some electron density, that is going to leave this carbonyl carbon with a smaller partial plus, which makes this less electrophilic, which makes the carbonyl carbon less electrophilic, less reactive, less susceptible to nucleophilic attack. So in general, when we think about carboxylic acid derivatives, we know that we have our carbonyl carbon connected to an oxygen or a nitrogen or a chlorine, and all of these are more electronegative than carbon, so we should be talking about this situation. But let's look a little bit more closely. So we want to consider the details of the reactivity of different carboxylic acid derivatives. And to do this, we want to consider inductive effect. So remember Falkland-Birch, fluorine's more electronegative than oxygen, chlorine, nitrogen, bromine's much more electronegative than carbon, which is about the same as hydrogen. So the difference between oxygen and carbon is bigger than oxygen chlorine, bigger than oxygen nitrogen. So if we think about inductive effect, then here we would have our biggest dipole arrow. Here we would have a smaller dipole, and here we would have the smallest dipole. So just looking at this, we might expect esters to be the most reactive. But in addition to inductive effect, we must also consider resonance effect. So oxygen, although it pulls away electron density by inductive effect, it releases electron density by resonance effect. The similar size of carbon and oxygen means orbital overlap is going to be very effective, and so oxygen is really good at releasing electron density to carbon by resonance effect. Chlorine, not quite as good, so it's not much of a resonance effect. Nitrogen can also release electron density. So when we take into consideration both resonance effect and inductive effect, then we get a ranking in terms of stability. So acid chlorides are less stable than esters, which are less stable than amides. So chlorine pulls away electron density by inductive effect, does not release electron density very effectively, so that means this carbon has the biggest partial plus, and so it is the most electrophilic. In comparison, nitrogen pulls away not as strongly by inductive effect, but it also releases electron density pretty effectively by resonance effect. And so here we're going to end up with a smaller partial plus, making this less electrophilic and so less susceptible to nucleophilic attack. So the stability of carboxylic acid derivatives has to do with the amount of partial positive charge on the carbonyl carbon. Now, what does that mean then in terms of relative reactivity of carboxylic acid derivatives, specifically toward nucleophilic attack? Well, because the acid chlorides have the biggest partial plus, that makes them the most electrophilic, and so they are the most reactive. So acid chlorides are more reactive than esters, which are more reactive than amides. Remember, we also have to consider anhydrides, but let's think about an ester versus an anhydride. So in both cases, oxygen is going to be pulling away electron density from the carbon by inductive effect, and in both cases, oxygen can release electron density by resonance effect. But in the case of the anhydride, because the resonance is going to be going in both directions, that think of it kind of like a competition, right? The electrons can be over here or they can be over here, which means you're not going to have as much electron density on either side. So this overall is more of an electron withdrawing group than this, which means this carbon is going to have a bigger partial plus than this carbon. So now we can put all 4 of our carboxylic acid derivatives together, and we see that acid chlorides are the most reactive, followed by anhydrides, followed by esters, followed by amides. So on the left, with acid chlorides or acid bromides, the carbonyl is the least stabilized, it's the most electrophilic, and so it's the most reactive with a nucleophile. On the right, this carbonyl is the most stabilized because nitrogen's not pulling away electron density super strong, and it's giving back some electron density. So that makes this carbon less electrophilic, less reactive with nucleophiles. Now, another important result is that as we consider acid chlorides, anhydrides, esters, and amides, interconversion by nucleophilic acyl substitution works going to the right. So you can convert an acid chloride to an anhydride because you are converting the most unstable carbonyl into a more stable carbonyl. An anhydride can be converted to an ester because you are converting a less stable carbonyl to a more stable carbonyl. Right? Interconversion does not work going to the left. So now that we've considered the relative reactivity of some carboxylic acid derivatives, let's think about the nucleophilic acyl substitution reaction overall. So this reaction happens in 2 major stages. The first part is the formation of the tetrahedral intermediate, the addition part, and then the second stage is the dissociation of the tetrahedral intermediate, the elimination stage. If we think about a general carboxylic acid derivative reacting with a general nucleophile, our nucleophile will share its electrons with the carbonyl carbon, pushing these electrons up onto the oxygen, and we get an intermediate that might have different charges. Depending on the exact species in the exact conditions, we might have this one positive and this one negative, or we might have this one positive and this one neutral, for example. Then there will be some rapid proton transfer. So acid-base reactions, some base will pull off this proton, allowing these electrons to go back onto this atom. And meanwhile, this can grab a proton from some acid, and you end up with the alcohol. Now, we're not talking about having concentrated hydroxide and concentrated HCl. We do not have strong acid and strong base together at the same time. But this could be the solvent that can act as both an acid and a base. So some of the details of proton transfer and of the charge, these are going to be some of the differences that we're going to see with the nucleophilic acyl substitution. When it comes to the dissociation of the tetrahedral intermediate, once again, there's a couple different ways to think about this, but we might have a base that can grab off this proton, putting these electrons back in here to form the double bond, pushing out the Y group as a leaving group. And so this is going to be our byproduct, but this is the new compound. And so we have restored our carbonyl, but we now have a different substituent over here. Now, if we look more closely at the tetrahedral intermediate, we might have this species where one group is protonated. We might have a species in which everything is neutral, or we might have this species where one of these groups has a negative charge. Most likely, we're going to have a combination. So under acidic conditions, we would probably have a combination of these 2 species. And under basic conditions, we would probably have a combination of these 2 species. So as we look at the details of different mechanisms, you're going to notice some differences. Try to keep in mind, though, the big picture. Nucleophilic acyl substitution involves formation of a tetrahedral intermediate and dissociation of a tetrahedral intermediate.